Thanks a lot. Great. I'll look forward to seeing my slides shortly. There we go. Awesome. OK. So 4 things I want to talk with you guys about today. The first is I want to talk about some of the strengths and weaknesses of modern AI. And there's probably only going to be about 2 slides in this deck about Vicarious specifically, because I want to try and create as much value for you guys as possible. So I try to reverse engineer the talk I'd want to hear if I was in your shoes. So first, we'll talk about modern AI, some strengths and weaknesses, how I think you should think about AI strategy, and what I see is coming in the next 2 to 6 years on the AI frontiers that will have some impacts on your businesses, hopefully, and then some of my general lessons from building a hard technology startup. So let's start with strengths and limitations. And before I do, can I get a quick poll? How many people in this room feel like they could give a short, cogent explanation of how AlphaGo works? OK, maybe 10% of the room. Great. So for the other 90% of you, I'm going to give you an incredibly short tutorial on how AI works, where you'll be able to explain this to your friends. It's not actually how these systems work, but it's close enough that it may as well be. And for the 10% of you who raise your hands, forgive me for the next 3 minutes. Maybe you should just tune out, because it may upset you. So today's AI is deep learning predominantly, and it's all about pattern matching. If we're going to build an AI together right now to read handwritten digits, the first thing we do is we gather thousands of hand-labeled, human-labeled examples. So this is 6,000 examples of the number 0. This is 6,000 examples of the number 1, and so on and so forth, until we have 60,000 human-labeled training examples of different digits. And then when we see a new image, our system basically just compares it to everything in the training database and attempts to find any close matches. And lo and behold, here are a couple, and so voila, what we have is a 4. And if you want to take that system and scale it up from handwritten digits to photos, you do the same thing. So you take a photo like this one, you label it with corn, which is something that's in the photo, and then instead of 60,000 handwritten digits or training images, you show it a couple million. Each pixel is 1 training image. And then you have a system where you can show it a new photo, and it'll say this is a car. But because all it's doing is pattern matching, if you show it something like this, it'll say it's a bedroom pillow. And it may say that this is a jaguar, but it will have no idea what a drawing of the same picture is. And it will also say that these things are jaguars, even though you and I know they're not jaguars. And so that's basically how these systems work. I think there's a really interesting and direct parallel between the evolution of artificial intelligence and the evolution of animal intelligence that we can use to extrapolate some lessons. So if we go back 600 million years, we get the very first intelligent animals, things like sponges and jellyfish, flatworms. And then as time passes, the animals get more complicated. I would argue they don't get any smarter. So what we have is all about instinctual responses. In neuroscience, we call this the old brain. And it's about pattern recognition, stimulus and response. And then about 100 million years ago, a miracle happened. Evolution figured out a radically different architecture for intelligence called the new brain. It's what gave us primates, whales, and dolphins. And instead of being about stimulus and response, it's about causal reasoning. It's about what if and why. And I'm going to argue that AI today is in this big yellow box, and give you some examples from the animal kingdom and from the computer kingdom to illustrate that point. So, and to be clear, there's nothing wrong with the old brain, and there's nothing wrong with deep learning. It just has a set of properties. So old brain AI or old brain intelligence can navigate environments. It can hunt for food. It can reproduce. But it has some really important limitations that matter if you're building a company and you plan on using these techniques. So our old brain ancestors, to make a new old brain animal, you need a couple of 100 million years of training data. And then the resulting animal isn't going to generalize well to new environments. It's not going to learn new skills. And most importantly, it just gives the illusion of intelligence. It's not actually smart. It just gives the illusion of intelligence. And I'll show you what I mean. Because if you peel back the layer of what's going on a little bit, it's very easy to reveal that the animals aren't actually smart. And it has this architecture where some stimulus comes in, the animal has learned a bunch of heuristics, and then it performs an output. So these are baby geese. Baby geese make this noise. And scientists figured out that mother geese will actually love and care for anything that makes that noise. So you can take a tape recorder that plays that sound, and you can put it inside a taxidermy of a wolf, and the mother goose will love and take care of the wolf until the tape recorder runs out of batteries, and then she'll peck it to shreds. Another example, these are baby ducks. Baby ducks believe the first thing they see when they're born is their mom, and these ducklings happen to see a dog when they were born, and so they'll follow the dog everywhere as if it's their mom. And then frogs also have a circuit in their brains that says fire the tongue whenever you see this little pixel pattern. And so you can actually starve a frog to death in front of a phone. And you'll see the same kinds of behaviors in today's smartest AI systems, which isn't to say they aren't awesome. Like deep learning is awesome. It can do all kinds of different stuff. It can play games. It can control robots. But it has the same limitations as the old brain, which is you need a lot of labeled training data. And after all that work, you get a system that doesn't generalize well beyond what you've trained it on, and it really isn't understanding what it's doing at all. It's just doing stimulus and response, pattern matching. And it even has the same architecture as our old brain animal friends. So you look at this very famous example. This is DeepMind's Atari player. And let's talk about how it works. So if you want a deep learning system to play Atari, all you do is you, instead of showing it one frame from the game, you just paste 3 frames together into a single image. And then, if for perspective, if that's our 60,000 handwritten digits and that's our million training photos, you show it 50 million frames of a single Atari game. After doing a lot of 50 million frames worth of play, it starts to learn, well, if I go left, I lose points in this instance, or if I go left, I win points in this instance. And you can start classifying sequences of frames into go left frames and go right frames. And after 50 million of these frames, the system works pretty well. And keep in mind, after doing that, it has no idea what a paddle is or a ball, or even what its goals are. It's just regressing on frames. So if you want it to do something different, like play a game that's on a brighter board, you need to retrain it from scratch for another 50 million frames. Or if you want to move the paddle up an inch, you need to retrain it from scratch. Or really anything you want to do at all, you're going to need to retrain it from scratch. And so if we take the same system, we just make the game 2% brighter, it will do this instead. Now AlphaGo is actually the exact same architecture, just scaled up even more. So if we look at our input Go board like this, and now we have down there, the little dot is our 60,000 digits. This is the million photos. This is the 50 million Atari frames, and this is the billion Go boards. Let me run through that again. OK, billion Go boards. So now this is about the equivalent of a human playing Go for 3,000 years without sleeping. And after playing that much Go, you start to get the AI starts to be able to classify Go from a board to a percentage chance of winning or losing. And so you show it any new board, it can then search over all the successors of that board, grade them from really likely to win and really likely to lose, and then pick the path that maximizes its chance of winning. So that's all it's doing. And if you wanted to play a different game, you're going to need another 3,000 years of training data. If you want to change the rules slightly, another 3,000 years of training data. If you just wanted to do something totally different, like fill the board with circles, you may as well start over, etc. So this is actually my favorite picture of the AlphaGo challenge match, because you can see that it's not playing Go. There's this guy who has to sit here to pick up the stones and put them on the board for AlphaGo because it's not capable of doing that. Which isn't to say that you can't use deep learning to control robots. You can. This is Google X, one of their most recent publications called the Arm Farm. And what they do is they're training these robots to pick up objects that are all about the same size. And to do that, you need about 2.8 million training images and 800,000 grasp attempts by running 14 robots for 24/7 for months. And then at the end of it, you get pictures like the ones on the left, and then you can go from picture to percent chance that you're likely to grasp an object, just like you did with the Go boards. And the problem is if you want to then, I guess there's a couple problems. The first is when it succeeds at grasping something, it's not because it had a good plan. Like it's doing something here. It happens to pick up the object, but not because it was particularly smart about what it was doing. And you see that over and over again in all the things that it does. So this is another example where you and I would make some different choices about how we were going to pick up this object, but it happens to work in the end, and so it's just fine. And the other thing is if you want to change the color of the bins that the objects are in, or if you wanted to pick up the objects from the side, or if you want anything to be different at all, you need another couple months and another 14 robots running 24/7. So deep learning, broadly speaking, is capable of combining lots of data and lots of computers and making really accurate, very narrow predictions. And that's not a bad thing. I mean, if I'm the CEO of Facebook or Google, what I have is a lot of computers and a lot of data. And what I want are narrow predictions about what ad to show you, or which of your friends might be in a photo or something. And so those are some of the strengths and weaknesses. Let's talk about how, if I were in your chair, I would be thinking about AI strategy. The first thing I would say is not having an AI strategy right now is a lot like not having a mobile strategy in 2010 or not having a web strategy in 2000. It's something that you probably already have. I hope you already have. If you don't already have it, make it your to-do list for this upcoming week. And the questions I'd be asking myself if I were in your shoes is, what am I predicting right now? Like, what is my product predicting? What is my company predicting? Where are there opportunities for me to inject prediction into my product or into my company? And then once you've identified opportunities where you could be making predictions, I would start thinking about what data sets you'd need to amass in order to be better at anybody else at making those predictions. Is there a way you can reframe what you do now as a series, as a pipeline of A to B mappings? Because that's really what deep learning does. It takes an input picture and outputs a label. It takes an input go board and outputs a % chance of winning. And so if you have anywhere in your product a pipeline of A's, B's, and C's and a chain, where is there value in filling in part of B or part of C that you don't have yet? And the next thing I would say is, if you can do this and do it well, you can build a data moat. You can build something that then becomes very difficult for competitors to catch up with you. So after you've decided what is the data set that I can collect, what is the prediction I want to make, then go back to your product design and look at opportunities to introduce features or user interface tweaks that cause your customers to interact with the product, and by virtue of their interactions, to create the data sets that you want in order to make your product win forever. So think about ways to incorporate labeling. And the last thing I would say is not to expect too much. So there's a really weird survivorship bias that goes on in deep learning, and particularly as you hear about in the media. So what you hear about in the media is how deep learning can do everything and how it's amazing. And what you're actually hearing about is how 1% of the time when someone tried this thing with it, it happened to work. And the other 99% of the time, no one wrote about it because it didn't work. And so I wouldn't have expectations that were too high of this technology. And I also think about this for almost every company as a win more or a win bigger kind of technology, and it's not going to make or break your company, but if you use it, you can definitely use it to widen your advantage over your competitors. So those are some thoughts. Let's talk about what's on the horizon. We're undergoing now, and what my company is part of, is this transition from instinctual-based systems to systems that focus on causality and mental simulation. And I want to emphasize that this is not a difference in degree. It's not you take AlphaGo and you scale it up to even bigger computers. This is a difference in kind. And to make a system that can be in a body and can make causal predictions about the world, you don't need deep learning. You need something a lot different and a lot, it takes a lot of R&D to kind of get there. And just like in the animal brain, the circuits that you see inside of a frog's brain and inside of a human's brains are basically unrelated. These technologies are very different. And I'll give you some examples from the animal kingdom and from the AI kingdom to draw the parallel. So killer whales in captivity are trained to pick up trash in their tanks and trade it with a trainer for fish. And one day a seagull died and fell into the tank, and the animal brought it to the trainer. And because it was like a big object or something, it got 2 fish instead of 1 fish. And you imagine a frog with 2 rewards would just eat both the rewards, and that would be that. That's not what the whale did. The whale did this with the second fish. And it repeated this over and over and over again and built up a stockpile of fish at the bottom of its tank. And then it used those fish to train all the other whales in how to participate in the seagull for fish economy. Next favorite example, this is Coco the gorilla. Coco was raised in captivity, and her favorite thing to do was watch, of all things, watch Mr. Rogers' Neighborhood. And for those of you who aren't from America, Mr. Rogers' Neighborhood is a very famous American TV program. Mr. Rogers every day sits down with the children, welcomes them to his house, takes off his shoes, and teaches them the lesson of the day. So Mr. Rogers found out that Coco was a fan of his show, and so he went to visit her at the zoo. And the first thing that Coco wanted to do with Mr. Rogers was help him take off his shoes, because that's how he always started his program. Okay, last example. This is an 18-month-old human, and it's being put into an environment it's never seen before, full of objects it's never seen before. It's watching a human it's never met before do an action it's never seen a human do before, and it's given no instructions.
Oh.
Oh. So, so why is it that we're able to do this stuff? Why can mammals perform feats that are so different from our animal ancestors? And the answer is we have a really different architecture for intelligence in our brains. We still have the old brain, the reptile brain. We use it to regulate our heartbeat and our breathing and our immune system. And then on top of it, we have a really different circuitry called the neocortex. It's a replicated circuit, and it's what does everything we consider intelligence. So it handles speech and vision and planning and motor actions and language. Everything happens in the neocortex, and it's the same circuit basically that does all those different things. And the only mammals have one of these, and it's the same architecture across mammals. And interestingly enough, it basically has the opposite characteristics of deep learning. So it takes very little training data, it generalizes incredibly well to out-of-sample environments, and it learns this rich causal model of the world, which when you're talking about robots and bodies is the most important thing. You need to be able to reason about what if and why. And in comparison to a deep learning or old brain system, your architecture in the new brain is this rich mental simulator. Like right now, you could close your eyes and imagine what it would be like to drive to the airport in a watermelon. And you could do it because inside your brain is a complete simulator of reality. And so that's what a new brain architecture is designed to do. And to give you a glimpse of like, what does this get us, I'll introduce a little bit of paradox, which is right now we're living in a world where all the parts that go into robots are really cheap. Like motors and sensors, plastics, metals, actuators, electricity, processors, all of that stuff is very affordable, and nobody owns any robots. And if you look at a factory 100 years ago and a factory right now, I mean, nothing's changed. It's color. Color is the only thing that's changed. And we pay people billions of dollars a year, maybe trillions of dollars a year, to do tasks that robots have been able physically to accomplish for decades. Across every industry, you know. It's so far from the future I thought I was going to live in when I was a 10-year-old. Maybe all of us thought we were going to live in. I thought I was going to have a general purpose robot that could do all kinds of different stuff. And the reality is we do have general purpose robots that can do all kinds of different stuff. This is a video from 12 years ago. And the trick of this video is the robot's being controlled by a human. So as long as you have a human brain, you can do anything you want with a robot. Like, if I force you to live your everyday life using a normal robot gripper, I think you could do 90% or more of what you do during your day-to-day routine. So functionally, we're already living in the Jetsons society. We're just missing the AI layer, the brain necessary to make robots useful and universal. And that is the product that Vicarious is working on. I think of it like Intel Inside for robots. And it's just an AI platform where you give it any combination of arms and grippers and sensors and tasks, and it just works. I think that interesting companies exist to make a prediction about the future come true. The prediction that I exist to make come true is to make a world where robots are as commonplace as cell phones. And I think you can reason about what the future might look like in just one chart. The top line is labor costs, and the bottom one is robot prices, indexed from 1990 onwards. And this is the only sort of Vicarious specific slide. We have a technology we've been building for 8 years now that is about 1,000 times less training data than deep learning and is a lot better at generalizing. So moving on from Vicarious, let's talk about what this means societally and what this means maybe for your business. So this is a picture. I love this pair of pictures. So this is 2005. This is the inauguration of Pope Benedict. And I'm going to show you another picture from 8 years later, and maybe you can tell me what's different about these two pictures. So the point I like about these two pictures is it's amazing how fast technology changes. Like, you know, we all live in Silicon Valley, or most of us do, and I didn't notice this happening. I mean, I noticed it happen, but I didn't realize how dramatically different the world is now than it was, 8 years before. And I think that we're on the precipice of going through a similar transition, a golden age of autonomy, a golden age of robots. And I'll give you some examples. So you've probably seen some of these videos, but let's just put them all together and get a glimpse into what the future might look like. So that was a four-legged robot from Boston Dynamics. These are two arms from Universal Robots. These have been out for years. I have a whole bunch of these at my office. These are bipedal robots from Agility Robotics. Pay attention to the gripper in this one. This is a 5-fingered human-scale anatomically correct gripper with touch-sensitive pads in all the fingertips. This is another one that's been out for a few years. This is a similar hand, except the actuators are powered by air instead of by motors. This is the commercially realized version of that same technology where it's being used to pick tomatoes. This is another bipedal robot from Boston Dynamics. So we're heading towards this world where robots become a lot more universal, where the automation not of ideas of information, the automation of labor becomes much more prevalent. And so I think of today, the cost of compute is basically electricity plus epsilon. And I see in the future, the cost of labor becomes electricity plus some epsilon. And I think there's actually this really interesting parallel between robotics right now and computing in 1950. Whereas if you wanted a computer in 1950, it was going to be expensive, inflexible, bespoke, and nobody really owned them. They were like very rare pieces of industrial equipment. And that's functionally what robots are right now. And I think in 2035, robots are going to be a lot like computers are right now. And then the natural question is, what does this do to the labor market? And I think if you ask the internet, you get all these headlines about how this means no one's going to have any jobs anymore, we're all screwed, the economy is going to collapse. And from my perspective, I'd like to introduce a counter-narrative. And maybe you've seen some articles that say things like we're being afflicted with a new disease, namely technological unemployment, where jobs get automated and people can't find new jobs. Does anyone know when this article was written? Guesses? 1930. So this is not a new fear, not a new concern. And I think that if we zoom out, the last 3,000 years are a story of people making contraptions that take a job that used to take 5 people a day to do and turn into a job that takes 1 person a couple of hours, a couple of minutes to do. And so the argument that this time is different, that this kind of automation technology is going to bankrupt the world's labor force, there's a very high standard of proof for this time being different. I think our best parallel is the agricultural revolution in the 1900s, where the US working age population went from 40% being on a farm to 2%. And the result of that transition was not mass unemployment. Every decade since 1890, roughly, the labor participation rate has gone up and not down. So I really think that this change is not going to produce an economic catastrophe. I think it's going to produce a lot of opportunities for people who are well situated to capitalize on them. And so I think of the opportunities this creates. I think there's actually going to be a lot of winners and a lot of new businesses that are built on top of this autonomy revolution. So strictly as the antecedents to the revolution, I think there's going to be a lot of winners in the enabling technologies. So sensors, processors, data, all of those things become more valuable when autonomy becomes more affordable. So being part of this ecosystem. And the other thing I would say is when you bet on labor getting cheaper, what does that do for your business? What does it do for substitutes to your business? Because maybe your business is designed around labor being a certain price. Is there an assumption underlying your bets? And also think about where are you using labor now and where could you use labor? If free labor existed, you could just turn it on like water, would you do something different in your business? And how does that factor into the strategy and choices you make in the long term? And then the last thing I'll say is just a couple of lessons from building Vicarious. So we're 8 years in and over 100 million raised so far. And I think if I had to distill it, this slide would be 100 pages long, but just 3 lessons from me. One is about explicitly managing technical risk. The other is being willing to look wrong. And the last one is on burn management and fundraising strategy that I think is a little different from hard tech. So in terms of managing technical risk, most startups are testing hypotheses about what users might want to buy. And for tech startups, or for hard tech startups, is the opposite. It's like you're building a time machine. You know people want to buy a time machine. The question is, can you make a time machine? And so I would think very, very carefully about how you know what you think you know, and what premises, if wrong, would be most damaging to your timelines. And lastly, I would think about future investors and where they're most likely to be skeptical and need a lot of audience to be convinced, and evidence to be convinced. Because if you are working backwards from your next fundraising milestone, you need to have expectations about where the burden of proof is going to be highest, and to some extent design your roadmap around meeting their objections, not just yours. The second thing is about being willing to look wrong. These are some quotes from different eras. Thomas Edison, fooling around with alternating current is just a waste of time. Nobody will use it ever. This is about Tesla in 2008. Tesla is in the business of bullshit, not cars. Never trust a software guy with a hardware deliverable. The sentence after this is SpaceX, same story. There's a nice one about us too. So get used to people hating you, because if you're doing something unique and different, you're going to attract detractors. I think of startups as arbitrage between what looks like a good idea and what's actually a good idea. And so if you've hit the sweet spot right, then you're probably going to attract detractors. The last area I would pay attention to is about burn-in fundraising. So if you're doing a hard technology startup, you're always going to be higher risk than Pinterest or Stripe or something with traction, because all of your milestones are around technology, not around customers, and that means you're going to have to make the VCs work a lot harder to understand your business, and they're going to make you pay for the cognitive load that you introduce into their deal-making process. And so, okay, we're done. And so I would say for this, timing is actually everything. You know, you have to plan to be alive long enough to get the right timing window when VCs happen to have bandwidth to think about hard technical problems. If you're trying to raise in the middle of when some other hot, very easy to assess, like Lime Bike kind of startup is out there, you're gonna hit more headwinds because they have a payback period of a month and a half, and the customers go like this, where you're like talking about something that's very technical, very complicated, and you need a PhD to understand it. And the last thing I would say is get really good at explaining why your thing is unique. And I know it's like obvious advice, but I've seen a lot of hard technology pitches because, for whatever reason, people tend to come to me and ask them about their pitch. And over again, what I see is something that doesn't sufficiently explain to a VC that doesn't have a lot of time why what they're building is necessary and different on the right level of abstraction. And the first part of this presentation, talking about deep learning, it's sort of educating you, is the first part of my VC deck. It's like a lot of my VC deck because investors need to understand in their language, in simple language, in really basic language, what is different about your technology from everything else. Can you wire him his money? And then the last thing I would say is recruit independent allies. So no one is going to believe your word about why your technology is good. Like, the investors are going to need some confidence that what you're doing is not just unique, but other people who are more experienced in the art and the practice of what they're doing is actually a really good idea. And so you need at least a couple of professors, a couple of independent thinkers who are well respected in the community to be able to look at what you're doing and say, hey, this is really different, and it's worth taking a look at or worth placing a big bet on in order to give investors some confidence in what you're doing. So those are some thoughts on burn-in fundraising. Thanks a lot for your time and attention. Happy to take some questions.
As sad as I'll be to see Scott leave the stage, I think we probably have time for maybe one or two questions.
No, I think you did an amazing job explaining the old brain, but I got a little lost on the new brain. Like, what is it that's so special about what you do that explains how you come up with a new brain?
Yeah, I mean, these are the cut slides, basically. I wanted to make room for strategic advice. There's a bunch of papers at Vicarious.com you can read. We had a science paper last year that went into more detail about it. I would say algorithms are only as powerful as the assumptions that are baked into them. MP3 is good at compressing sounds because it assumes you're a human, you're listening to music, and so you're probably the same sound in both ears and a bunch of other things. So the strength of deep learning is also its Achilles heel. Deep learning you can use for anything because it's just doing function approximation. Whereas our brains as humans, we become pre-baked with a bunch of inductive biases, like the pixels that make up my face aren't teleporting at random all over the room. They tend to stay together. They stay together over time. When you move your head in a particular way, the room transforms itself spatially in the same way every time. There's all these biases that evolution baked into our brains to make us efficient learning and great at generalizing. And those are the biases that we encoded into our algorithms that make them better at deep learning at this particular task, which is embodied robotics.
What other companies, apart from OpenAI, DeepMind, and probably you, go after solving AGI? And if that's it, then why there's so few? And why is OpenAI so afraid of that? Like, literally, people working there are terrified about AGI.
So there's so few because I would say it's very capital intensive and expertise intensive. You can't be an AGI company with 3 people and 2 years of runway. It's just not credible. And so I think there's very few of them, just like there's very few space exploration companies. It's incredibly expensive. It's a multi-discipline coordination problem. And then in terms of OpenAI, why are they so scared of it? So OpenAI has a belief, actually, and I think DeepMind does too, that if you scale up the old brain enough, you get to the new brain. And this is something that I don't believe and disagree with, which is why I'm not nervous at all about what OpenAI is doing. I think they can do it forever, and it never scares me because I don't think they'll just get super intelligent crickets. And so I think that's the direction. And if I believed what they believe, I would be super scared, right? I'd be scared of the crickets taking over the world. But I think that particular AI strategy is not likely to get to a new brain-like architecture, and so that's why I personally don't worry. But I understand why they're scared.
And last question.
So with your strategy, when do you think we will get to human-level AI, and what do you think about super intelligence?
I think that superintelligence is inevitable when everyone's wrong when they make guesses about this stuff. I'm not going to throw my hat in that ring. I mean, I think it's going to take as long as it takes, and hopefully we'll be the ones to do it.
Thanks a lot, Scott.
Thanks a lot,
Appreciate
Samir.